Derby, England, late 1937. Stanley Hooker was 30 years old, a mathematician who had never, in his own words, seen an aero-engine at close range. He had been summoned from the Admiralty, where he'd spent 2 years doing anti-aircraft mathematics, by a letter from a former Oxford contemporary, Frederick Llewellyn Smith, by then a Rolls-Royce engineer, who had noticed that Hooker's published academic papers might be relevant to a problem the company needed to solve. The interview was with Ernest Hives. Hives was 51 years old, had started at Rolls-Royce as an experimental tester in 1908, and had risen through 3 decades of practical work to become general manager of the Derby Works, effectively the most powerful executive in British aero-engine manufacturing. He carried no university degree. He had self-taught skills, a career built on reading machines through physical contact with them, and a talent for identifying people who could solve problems that had resisted his engineers. He had copies of Hooker's published academic papers on his desk when Hooker walked in. He thumbed through them. He asked one question: "What's a Kármán vortex street?" Hooker explained. A Kármán vortex street is a periodic pattern of alternating eddies that forms when fluid flows around a bluff body. Predictable, describable in closed-form equations, the kind of thing a fluid dynamicist knows instinctively and a mechanical engineer might spend half a career articulating. Hives leaned forward and told Hooker he wasn't much of an engineer. He hired him on the spot. That exchange is the structural spine of everything that follows. Hives wasn't being dismissive, he was being precise. The engineers around him at Rolls-Royce thought about machines as mechanical assemblies, geometry, tolerances, metallurgy, test results. Hooker thought about machines as mathematical objects, flow fields, pressure ratios, dimensionless groups, efficiency curves with theoretical optima. Hives, who had spent 30 years testing the gap between what an engine did and what it should do, understood immediately that this wasn't a deficit. It was exactly what the supercharger problem required. 5 years later, Hooker had designed the 2-stage, 2-speed supercharger fitted to the Rolls-Royce Merlin 61. That engine gave the Spitfire 9 a critical altitude of 23,500 feet, several thousand feet above where the Focke-Wulf 190 could fight effectively, and restored British air superiority over occupied Europe at the moment it had most genuinely slipped. 22 years after that, the same mathematical approach to an entirely different problem produced the Pegasus, the 4-nozzle vectored thrust turbofan that made the Harrier the world's first operational jet-propelled vertical takeoff aircraft and powered it through the Falklands. He titled his autobiography after the worst thing Hives ever said to him. Stanley George Hooker was born on September 30th, 1907 in Tiverton, Devon. He won a scholarship to a grammar school, coasted through his early years on minimal effort, then committed briefly to one examination, the London University matriculation, and scored well enough that the school was granted a half-day holiday in celebration. In 1926, he arrived at Imperial College London on a scholarship, where the assistant professor of mathematics, Hyman Levy, directed him toward the study of eddies produced when solid shapes move through fluids. That subject is worth understanding precisely. The mathematics of fluid flow around objects, how air separates, swirls and loses energy as it passes a curved surface, describes everything from the drag on a wing to the pressure distribution inside a supercharger impeller. Hooker was learning to think about machines in terms of flow equations rather than mechanical geometry. He won the Busk Studentship in Aeronautics in 1928 and moved to Brasenose College, Oxford, where he pursued mathematical analysis of air density, compression, and high-speed compressible flow. His D.Phil, completed in 1935, addressed fluid mechanics at the boundary between subsonic and supersonic conditions, the behavior of air as it approaches and passes through the speed of sound. He was working at precisely the theoretical frontier that supercharger designers would need to cross as power demands pushed impeller tip speeds towards sonic limits. The application wasn't visible to him yet, but the toolkit was already there. After Oxford, Hooker reported to the Admiralty, working on anti-aircraft mathematics. Llewellyn Smith's letter arrived in the autumn of 1937. His published papers had been noticed. The path from the Admiralty to Derby was settled within weeks. The autobiography's account of the first day at Rolls-Royce is specific enough to feel like memory preserved. A damp, cold morning in January 1938. Walking along Nightingale Road toward the Great Works. Being shown into an 8-foot square office containing a desk, a bare bookcase, and a telephone, and then left, as he described it, utterly alone. For several days he read the Times. Eventually he walked into the surrounding workshops where young engineers bent over drawing boards and tried to understand what they were doing. His formal assignment, when it came, was the Supercharger. The Merlin's single-stage centrifugal supercharger in 1938 ran one impeller at roughly 28,000 revolutions per minute, approximately 9 times engine speed, forcing compressed air-fuel mixture into the cylinders. The compression ratio was approximately 3.5 to 1. On 87-octane fuel, the maximum safe boost pressure was around plus 6 pounds per square inch. The Merlin 3 produced 1,030 horsepower at 10,000 feet and declined markedly above that altitude as thinning air reduced the mass of charge the impeller could deliver. What Hooker brought to this machine was non-dimensional analysis, a technique from fluid mechanics that groups a system's variables into dimensionless ratios, revealing the machine's fundamental behavior independently of its specific operating conditions. Applied to the Merlin supercharger, it allowed him to map actual performance against the theoretical efficiency envelope and identify precisely where the gap lay and why. The engineers around him had been improving superchargers empirically. Change a dimension, run the test, measure the output. Hooker calculated what the change should produce before the test was run. The difference wasn't only accuracy, it was speed of development. The redesigned supercharger in the Merlin 20 incorporated revised inlet geometry and improved guide vanes on the impeller, based on those calculations. Rated output rose to 1,240 horsepower at 10,000 feet in low gear and 1,175 horsepower at 17,500 feet in high gear, both at plus 9 pounds per square inch boost on 100-octane fuel. That is a 20% power increase at altitude from the same cylinder displacement, achieved through flow analysis rather than increased fuel. The Merlin 20 entered production in the Hurricane 2, the Lancaster 1 and 3, and the Spitfire 5. Hives formally transferred charge of all supercharger development to Hooker. The autobiography records the moment. From now on, Hooker was in charge of supercharger development. Not much of an engineer, in charge of the most consequential subsystem in British air power. The Battle of Britain was fought in the summer and autumn of 1940, primarily with single-stage Merlins. Hooker's first-generation improvements were in service, contributing real horsepower to real battles. But the crisis that would define his career, the one requiring not an improved single-stage engine, but a completely different architecture, was still coming. It arrived in September 1941, over the coast of northwestern France. The Focke-Wulf 190 appeared that autumn, and the RAF pilots who encountered it sent back reports their commanders initially struggled to accept. The aircraft outperformed the Spitfire 5, then Britain's best operational fighter, in every category except turning radius. At 2,000 feet, it was 25 to 30 miles per hour faster. At 3,000 feet, 30 to 35 miles per hour faster. Even at 15,000 feet, its narrowest margin, it held a 20-mile-per-hour speed advantage. Its roll rate was superior enough that a Spitfire 5 attacking it could watch the German pilot roll into a dive in the opposite direction and simply accelerate away. RAF pilots flying cross-channel sweeps began taking casualties that no change in tactics could explain. Air Marshal Sholto Douglas, commanding Fighter Command, put his concern explicitly on record. The Merlin engine Spitfires had approached the limit of their single-stage development potential, while the FW-190 was only beginning its career. He feared the technological edge had crossed over. In June 1942, a Luftwaffe pilot partially resolved the intelligence gap by accident, becoming disoriented in cloud and landing his FW-190A intact at RAF Pembrey in Wales. British test pilots flew the aircraft immediately. The evaluation confirmed every combat report. Ernest Hives wrote to Air Chief Marshal Freeman. He already knew where the answer was. The FW-190A's BMW 801 radial engine gave it dominant performance at low altitude, with a secondary capable band around 20,000 feet, before weakening sharply above that. The engine's single-stage supercharging couldn't sustain rated output in the thinner air above that altitude. If the Spitfire could be made to perform where the German aircraft struggled, it could dictate the terms of the engagement. That meant altitude. That meant a fundamentally different supercharger design. Hooker had started building it 2 years earlier. In 1940, the Air Ministry had requested a turbocharged Merlin for a high-altitude Wellington 6 variant. Hooker declined turbocharging. His objection was precise. Rolls-Royce had patented the ejector exhaust system in 1938, and an exhaust-driven turbocharger would consume the exhaust flow and eliminate the additional thrust those ejectors generated. He proposed 2 centrifugal supercharger stages in series instead. The principle: the first stage compresses the incoming air-fuel mixture. An intercooler, a liquid-cooled heat exchanger mounted between the stages, removes the temperature that compression adds. A second, smaller diameter impeller then compresses the charge again before it enters the engine. The intercooler is essential. Without it, the doubly compressed charge is too hot and too expanded to deliver full weight per unit volume into the cylinders. With it, the charge arrives dense and at a manageable temperature at altitudes where a single-stage engine has already given up. The Merlin 61, first of the 60 series, combined both stages with a 2-speed drive, a moderate gear ratio for lower altitudes and a high gear for altitude work. The compression ratio rose from approximately 3.5 to 1 in the Merlin 3 to approximately 6 to 1 in the Merlin 61. The engine's critical altitude, the highest point at which it produces full rated power, was 23,500 feet at 1,390 horsepower in full supercharger gear. The Merlin III had made 1,030 horsepower at 10,000 feet and declined from there. That isn't an incremental improvement. That is the same basic engine family operating at a completely different part of the atmosphere. The engineer published the first detailed public description of the Merlin 61 in its December 1942 issue. The article noted that a Spitfire fitted with the engine had already destroyed 3 German Junkers Ju-86P stratosphere reconnaissance aircraft above 40,000 feet. Aircraft the Luftwaffe had been operating in the confident belief that nothing British could reach them. It also recorded, with the precision of a technical press that understood exactly what it was reading, that the power of the original Merlin III engine had been doubled. The Spitfire 9, fitted with the Merlin 61, entered operational service in June 1942. The RAF's Air Fighting Development Unit conducted formal comparative trials against the captured FW-190 in July 1942. At 8,000 feet, the Spitfire 9 was 8 miles per hour faster than the FW-190. At 15,000 feet, 5 miles per hour faster. At 18,000 feet, the margin widened further. At the altitudes above 20,000 feet, where the FW-190A's Supercharger system could no longer sustain its rated power, the Merlin 61 was still operating well within its design envelope. The aircraft that had sent shock through Fighter Command in September 1941 now faced a British opponent that held the performance edge at every altitude where RAF pilots could choose to fight. From a calculation, from a mathematician applying dimensional analysis to a problem that practicing engineers had been solving by iteration, came the architecture that shifted the terms of the air war over occupied Europe. The Merlin 61's design propagated through every aircraft that flew the engine in its later forms. High-altitude Mosquito variants, the pressurized Mark 15, and later reconnaissance versions used to overfly German-held territory, flew with Merlin 72, 76 and 77 engines, all 60 series, all carrying the 2-stage Supercharger. Their operational ceilings extended well above the range of the interceptors sent against them. The Lancaster primarily flew with Merlin 20 and 22 series engines, which carried Hooker's first-generation single-stage improvements. A different set of figures, but still Hooker's analysis embedded in every sortie of Bomber Command's offensive. The most consequential application of the 60 series engine happened in an American aircraft. The North American P-51 Mustang had been built around the Allison V1-710, an American engine with a single-stage supercharger that performed well below 15,000 feet and fell apart above it. As a long-range escort for B-17 and B-24 bombing targets deep inside Germany at 25,000 to 30,000 feet, it was operationally inadequate. Packard Motor Car Company held a U.S. license to produce the Merlin, and the P-51B flew with the Packard V1650-3, equivalent to the Merlin 61 series. With the 2-stage Supercharger, the Mustang's effective altitude extended above 40,000 feet. Its exceptional range could now be fully used at the altitudes where the strategic bombing campaign desperately needed fighter cover. American bomber crews who had been flying unescorted into Germany suddenly had a fighter that could go where they went and hold its own in the thin air above 30,000 feet. Hooker had designed the Supercharger. Everything else was already waiting for an engine that could use it. In September 1948, on his 41st birthday, Hooker had his final meeting with Ernest Hives. Rolls-Royce, after 1945, had been reorganizing its jet engine work.
Hooker had spent the later war years at the company's Barnoldswick factory in Lancashire, taking over Frank Whittle's jet programme after Rolls-Royce reached its 1942 deal with the Rover Company. The arrangement had been finalised over a wartime dinner, Hives trading a tank engine factory for the jet engine factory, telling the Rover directors they were playing around with something that wasn't in their line. Hooker had industrialised Whittle's concepts at Barnoldswick, producing the Welland engine that powered the Gloucester Meteor, then the Derwent, and beginning work on the Nene. But Rolls-Royce was centralising its jet work at Derby, and Barnoldswick's role contracted with it. Hooker had expected to be appointed chief engineer of the unified jet operation. He wasn't. The autobiography describes the rupture with characteristic directness. Rancorous. He worked out his notice and arrived at Bristol Aeroplane Company's engine division in January 1949. The dust jacket of his own autobiography captured what followed. He tugged a rather reluctant company into the jet age, determined to give real competition to Rolls-Royce. The Proteus turboprop, intended for the Britannia airliner, was in serious difficulty. The Olympus turbojet, which would eventually power the Avro Vulcan and Concorde, needed direction. Both were sorted. In 1952, Hooker produced his first entirely original engine design, the Orpheus, 5,000 pounds of thrust, built for the Folland Gnat lightweight fighter, which went on to become the standard engine for NATO's Fiat G91 ground attack aircraft and saw service across multiple air forces. Then, in May 1957, Sidney Cam wrote from Hawker Aircraft. Cam had designed the Hurricane and, since the war, the Hunter, one of the most successful post-war British fighters. He was looking for a Hunter replacement. He'd heard about work at Bristol on a vectored thrust engine called the BE-53. Could Hooker tell him more? The concept had originated with a French aircraft designer, Michel Vibol. In 1955, Vibol had proposed using 4 centrifugal blowers, with exhaust rotatable between downward for lift and rearward for flight, to achieve vertical takeoff. The core idea of vectoring thrust was original. The proposed power plant was far too heavy to be practical. Gordon Lewis, an engineer at Bristol working under Hooker's technical direction as the company's technical director, had spent 1956 rebuilding the concept entirely from Bristol's existing components, Orpheus core, compressor stages from the Olympus, into something that might actually fly. What emerged was the 4-nozzle configuration. Instead of rotating the engine or using separate lift power plants, the BE-53 used a single turbofan with 4 swivelling nozzles, 2 at the front of the engine fed with cool fan bypass air, 2 at the rear discharging hot core exhaust. All 4 nozzles rotated simultaneously through 98.5 degrees, from pointing rearward for conventional forward flight, through downward for vertical takeoff or landing, to intermediate positions for transition and deceleration. The airflow split was roughly 60% through the front cold nozzles, 40% through the rear hot nozzles. Nozzle movement was driven by motorcycle chain mechanisms running from air motors, straightforward, light, and field maintainable. One design feature took careful thought to arrive at. The Pegasus's low-pressure and high-pressure spools rotate in opposite directions. This isn't the default arrangement for a turbofan, and it required specific engineering choices to implement. The reason is angular momentum. In a single-shaft engine hovering vertically, the rotating assembly creates gyroscopic torques that impose pitching and yawing moments whenever the aircraft changes direction. Counter-rotation cancels those moments and leaves the pilot with a controllable aircraft. Understanding why this was essential,
thinking about a jet engine as a system of angular momentum vectors rather than a sequence of mechanical stages, required a mathematical physicist's instinct, not an engineer's. The first prototype ran in 1959, producing approximately 9,000 pounds of thrust. By October 1960, the first flight standard engine had been delivered to Hawker's Dunsfold factory at 11,300 pounds. The Hawker P1127, designed by Cam's team around the engine, made its first tethered hover in November 1960. Transition from hovering to conventional wing-borne flight was achieved on the 8th of September 1961. The RAF initially described the whole concept as a toy and a crowd pleaser. Then the thrust grew. Pegasus 3, 13,500 pounds. Pegasus 5, used in the Kestrel evaluation aircraft trialled by 9 NATO nations, 15,000 pounds. Pegasus 6, powering the initial production Harriers that entered RAF service in 1969, 19,000 pounds. Pegasus 11 Mark 103 for the Harrier GR3, 21,000 pounds. The Sea Harrier FRS-1, built for the Royal Navy, flew with the Pegasus 14, the Mark 104, a navalised version with corrosion-resistant components, at 21,500 pounds. From the first engine run in 1959 to the Sea Harrier in Royal Navy service, the same basic 4-nozzle architecture, developed across 20 years of refinement, had grown from barely enough to lift a prototype off the ground to a front-line naval combat aircraft. On April 2, 1982, Argentine forces landed on the Falkland Islands. Britain assembled a task force and sailed south. HMS Hermes and HMS Invincible carried 28 Sea Harrier FRS-1 aircraft, each powered by the Pegasus 104, producing 21,500 pounds of thrust. The South Atlantic is a demanding operational environment. Salt spray, high humidity, wide variations in ambient temperature, sustained sortie rates over 10 weeks of combat at sea. The Pegasus engines performed. The losses the Sea Harriers sustained came from surface-to-air missiles and anti-aircraft artillery, not from Argentine aircraft in air-to-air engagements. Against Argentine Mirages and Daggers, the combination of the AIM-9L Sidewinder missile and the thrust-vectoring maneuverability the Pegasus enabled, the ability to bleed speed rapidly, force an overshoot, and turn inside an opponent, proved decisive at sea level over the South Atlantic. Hooker was 74 when the war ended. He had been ill for 2 years. He was finishing his autobiography. Sir Stanley George Hooker died on 24 May 1984 in Bristol. His autobiography, Not Much of an Engineer, was published by Airlife the same year. He had been knighted in 1974, elected to the Fellowship of the Royal Society in 1962, and awarded the Royal Aeronautical Society's Gold Medal in 1967. The Royal Society presented him with the Leverhulme Medal in 1981. The Wilhelm Exner Medal followed in 1982. Gerhard Neumann, who had run General Electric's jet engine operations for 2 decades and knew every major name in the field, wrote the National Academy of Engineering's memorial tribute. He called Hooker a giant in the field of aircraft jet propulsion, and added a precise observation. No account of the growth of the industry would be complete or accurate without paying tribute to his accomplishments. Test pilot Bill Bedford, who had flown the P1127's first tethered hover at Dunsfold in November 1960, gave a talk in London in the late 1980s. At the end, he showed a photograph of Hooker on the screen behind him.
He said he'd have to think about it, but if asked who was Britain's greatest ever engineer, he'd have to decide between Brunel and Sir Stanley Hooker, and he'd probably go for Sir Stanley. The autobiography's title came from the interview in Derby in late 1937. Hives, the published papers on the desk, the question about the Carmen Vortex Street, then leaning forward. Hooker chose to put that remark on the cover of the last thing he would ever publish. Not as a wound, as an argument. The industry had spent 4 decades asking him to solve problems that qualified engineers couldn't solve, and every time he'd solved them by thinking like a mathematician rather than an engineer. He thought Hives's observation deserved to be the final word. The Merlin he improved remained in operational frontline service through the Korean War. The Pegasus he developed powered Harriers in combat across 5 conflicts over 30 years. He carried no aeronautical engineering qualification when he walked into the Rolls-Royce works in January 1938. He won every significant award the British and American aerospace industries could give him. The book is still in print. Subscribe for more stories like this.